All right. Hello, everyone. Thank you for joining us and welcome to the APS DGRAV seminar series. Today we have Salvatore, Vitale, and Sylvia Biscoveanu joining us today to speak to us. Dr. Vitale joined MIT's physics department as a professor, before which he did his PhD at the Pierre and Marie Curie University in Paris. And before that, he obtained a bachelor's and master's from the University of Bologna. And he does gravitational wave analysis for LIGO Lab with interests in parameter estimation for black holes, tests of general relativity, as well as measuring neutron star equation of state. Sylvia is a PhD student at MIT and a Soros Fellow, as well as a National Science Foundation Graduate Research Fellow. She also works on gravitational waves with interests in parameter estimation for compact binaries, multi-messenger astronomy, and stochastic gravitational wave background. Before MIT, she did her undergraduate studies at Pennsylvania State University. And before starting the PhD, she also did a Fulbright postgraduate scholarship at Monash University in Melbourne. Today, these two will speak to us about the spin of binary black holes following LIGO and Virgo's third observational run. Thank you. Take it away.
All right. Thank you, Dalia, and everyone for having us here. And so in particular, Kent and the other friends at APS, and to you all for attending. Let me share my slides. So the plan is that I will talk for roughly 20 minutes. I'm going to start the timer now, and then Sylvia will take it from there. So as it was just said, the main focus of my work and the topic of today's presentation, it revolves around the measurements of compact binaries parameters, in particular black hole spins for today. All right, so let me start, assuming I can change slide. Fantastic. So I'm assuming I don't really need a great deal of introduction about gravitational waves. I'll just have basically a slide to remind you that whenever two stellar mass compact objects merge in a binary, they emit gravitational waves throughout the whole process. And if they are of stellar mass nature, then the gravitational waves they emit during the last few minutes or seconds, depending on the mass, are detectable by gravitational wave detectors here on Earth, in particular the ones which are radioactive, LIGO, Virgo, and CAGRA. And here you see on the left a picture of LIGO Hanford in Washington State, and in the middle, artist representation of a merger or neutron star into a black hole. And on the right, an animation made by the SXS collaboration of the first gravitational wave detection in 2015. All right, so why do we care about this? Well, we care about this in particular about compact binaries because one of the things they allowed us to do is to try to understand the formation channels of compact objects and their progenitors. So in particular, what we would like to do, one of the things we would like to do, I should say, with these gravitational waves is to understand where and when in the history of the universe compact binaries form. And so what this means in practice is that we would love to measure things like the merger rate of compact objects as a function of the redshift of their masses and so on and so forth. And, once you have that in hand, you can go after more sophisticated and useful things like measuring the time delay distribution between the formation of the, black holes and their mergers and so on and so forth. And related questions that you can try to tackle are interesting from the astrophysical point of view. For example, we would like to understand whether all of the black holes at the LIGO, Virgo, CAGRA collaboration, and also I should say other groups using the public data are detecting, whether those black holes are all formed astrophysically in the same way. And if not, which is very likely, we would like to understand and measure what is the number and the characteristic of the astrophysical subpopulations that make our whole basket of compact binaries. And so the idea here, at this point, probably is clear enough, is that we would like to use the population of detected compact objects. In particular, today I'm going to focus on black holes, to say something about the underlying astrophysical formation scenarios that brought these two objects together. All right, so yeah, I can change slide. So how do we find out where our black holes come from? Well, we can rely on the fact that over the last few decades, there has been tremendous progress both on the theoretical and numerical point of view. And these days, we do have simulations, and here on the right, you see the logos of a few of these algorithms that can make these predictions. They're typically called population synthesis code, that can tell us or give us an idea of what properties compact binaries should have, depending on where and how they formed. And so in theory, what we need to do is very simple. We just have to compare these predictions with the properties that we are actually seeing in our data. And hopefully that way we can learn about the astrophysical origins of our objects. And in particular, there are typically two very broad categories of formation scenarios that people have in mind. One, it's formation in galactic fields, which basically implies that the two black holes were already two stars in a binary, and then one went boom, and supernovae left behind a black hole. The other did the same, and eventually these black holes merged. Of course, I'm making a very complicated story. Sounds very simple. In reality, there is a lot of physics and astrophysics that goes into this, which is somehow tackled by some of these codes. The other, possible way in which you can form a binary is that the two black holes become black holes independently. They were not in a binary at the beginning. They just became black hole, but they were black holes in a region of the universe where there is enough of those objects that the probability that two of them form a bound orbit, it's pretty high. And again, I'm making a very hard story, pretty simple. In reality, you typically have also 2 and 3 body interactions in this type of systems. And so if you ask yourself, where in the universe we have enough black holes that things like this can happen, we are thinking about clusters, globular clusters, nuclear star clusters, or more recently also formation within disks of AGNs as also being considered more and more carefully. All right, so I won't have time to go into the predictions that all of these codes make on the various properties of black holes that come through the various channels. I just made a very simple slide, and here, if there are people in the audience who actually work on this, they will have to forgive me because this is very crude. Here I have a table which basically splits the formation in the field on the left and dynamical formation on the right, and the various rows are some of the key properties of a binaries: the masses, mass ratio, spin magnitude, spin orientation, eccentricity, and redshift. And in a few words, I summarize, again, very roughly, what is the expectation for those properties depending on where the black holes binary are formed. And now, I won't go through all of it. The one pair I want to highlight, because it's going to be relevant for the rest of my and especially Sylvia's presentation, is that the spins of the two black holes, and in particular the spin orientation, can be used to distinguish pretty clearly formation in the field from formation in a dynamical environment, because in the latter case, you would expect the orientation of the two spins to be random, since the two black holes met randomly and formed a bound system, while in the case of a formation in the field where the two black holes have been together throughout their whole life as stars, various mechanisms and tides are expected to align the two spins by the time they enter into the LIGO band. And so, if nothing else, spin and spin orientation could be a good way of distinguishing between these two classes of astrophysical formation scenarios, which is nice. Now, in reality, it is challenging to do so because it's very hard to measure spins. So what I've done in this slide is to somehow rank the various key parameters of a compact binary in order of how hard they are to measure. So the chirp mass And if you want a definition, it's given here on this plot on the right. It's a combination of component masses and total mass. Chirp mass is the parameter that we measure the best of all. It's typically % for low mass binary black holes, and then it gets worse and worse to tens of % as the mass increase. Next up, the component masses or mass ratio, which is the same. They're typically measured at the tens of % level and worse when the two masses are comparable. And now we come to spins. The component spins are usually measured pretty poorly, and Sylvia will say something more about this later, unless spins are large and a few other things happen. Luckily for us, even though the component spins typically come with very large uncertainties, there is a particular combination of the two spins called chi-effective, which again is defined on the plot on the right in red. You can think about it as the mass-weighted projection of the total spin along the angular momentum, pretty much. Now, this parameter turns out to be measured much more precisely than either of the component spins, and surprisingly, even for large masses. And Sylvia, again, will get back to this point later. Next up, we have the spin tilt angle, so their misalignment, pretty much. And, or which is the same, the precessing total spin, which is the component of the total spin along the orbital plane you see here on the plot on the right. So this is basically, these are the degrees of freedom that would tell you something about misalignment between the spin and the angular momentum. And unfortunately, those are typically very poorly measured. And finally, we have the eccentricity, the orbital eccentricity, which it's even harder to measure unless it's very large. And even then, these days, we don't really have great waveforms to do so. All right, so I mentioned here what type of precision we can expect for the measurements of spins, in particular for individual sources. The reason why spins are harder to measure, say, than masses is because of the way they are encoded in the gravitational waveforms. So if you look at a waveform like the one I have here on the left, sorry, you know, if you have done this long enough, you can guess some of the properties of the source just by the morphology of the waveform, the way waveform looks. The same way, if you bring to someone who does CMB, a CMB spectrum, they can tell you something about the universe by every peak, you know, and throat. We can kind of do the same here. And so in particular, something like the duration of the signal tells you, gives you information about the total mass and the aligned component of the spin. The phase evolution gives you something at the lowest order about the chirp mass, then mass ratio, and only at that point spin. So you can really think about the phase evolution as a Taylor expansion on V over C. And so the higher the order, the harder the measurement. And spins turns out to be a much higher order than, say, chirp mass. The overall amplitude tells you something about the distance and inclination of the binary. And if, as in this case, you see orbital amplitude modulation, then you can infer that the spins were, say, precessing, or there was eccentricity in the binary. And finally, what we call the merger ring down, which is basically the last few cycles after the collision happens, can tell you something about the nature of the compact object. All right, so again, a lot of the information about spins can come from phase evolution, but also from amplitude modulation. And indeed, it was already remarked by Apostolados et al. In 1994, if I'm not wrong, that whenever there is spin precession, and so your orbital plane wiggles, as represented here in this cartoon, then you can measure spin better. And you can measure spin better if your line of sight is close to what we call edge on, which means that you're looking at the system from its plane, not from above or below. So if this angle iota gets close to pi over 2, that's when you can measure the spin the best. And the reason why that happens, it's because in that case, if there is precession again, you see a huge amount of amplitude modulation, and that helps you measuring spins because, among other things, it breaks the degeneracies. Let me show you this in practice. What I have here on the left, I'm going to talk about the plot in a second. What I have on the left is going to be a video in a second. It's the cross and plus polarization of a waveform. Cross is at the top and plus is at the bottom. There is some amount of precessing spin here. What the video is going to do once it starts is that it's going to show how those two polarizations look like when the inclination angle is varied. And let's see if that works. So as you should see, depending on what the orbital inclination angle is, what your line of sight is, pretty much, you get a huge amount of modulation in some cases, like now, but also very little or no modulation like now, okay? And again, the reason is that if the system is seen from face on, even if there were modulation, you would actually not see it very much. While if the system is close to edge on, any small amount of spin precession gives a very clear imprint on the waveform. And indeed, this has been found to be true numerically, among others by myself on the plot on the right, where we have on the x-axis the inclination angle in radians. So edge on would be 1.57 here. And on the y-axis, we have the uncertainty on measurement of the spin magnitude of the most massive object in the binary. And the various circles and points and whatever are different type of sources, I'm broadly dividing them in 3 categories. The ones at the bottom, which are basically horizontal lines, are systems where there is no precession to start with. These are just spin-aligned systems, and we can measure them pretty well when they're large. But the nice thing about this plot is that it shows with these square and triangles here that go down and then up, indeed that when you have spin precession and the masses are not equal, then you can measure spins a factor of 2 or 3 better if the system is oriented this way as opposed to this way. And so this seems like it's a nice thing. Then we just have to wait until we see a bunch of binaries that have orientations like this, and then we will measure spins with a very small uncertainty. Now, the problem, unfortunately, and that explains a lot of what LIGO and Virgo have published so far, is that most of the binaries we will detect in the next few years, they don't live here. They will live at the 2 edges of this plot. And the reason has been found, or among other things, I guess among other people, has been written nicely by Bernie Schutz a few years ago. So what Bernie has shown, and here I'm just re-representing in a different way, is that if the distribution in the universe of orbital orientation is isotropic, as it should be, then you would expect this green distribution, a sign of iota. But now, because emission of gravitational waves from the binary is not isotropic, most energy goes along plus and minus L, the distribution of inclination of the systems that are detectable becomes that blue dash line. So most systems that we can detect with LIGO and Virgo will have inclination around 30 degrees or pi minus 30 degrees, for which spins are hard to measure because even if there were precession, it would not be very easy to see in the detector frame. So that should explain why so far we have not really reported any uncontroversial measurements of large precession or anything like that. Okay, so very quick in the last few minutes, I don't want to live with a negative or pessimistic overlook, right? Because the truth is that even if parameters of individual sources may not be particularly easy to measure, we can still do a lot because what we can do is combine information, as I was mentioning earlier, from all of the sources that we are detecting and say something about the underlying population. This is typically called, technically speaking, hierarchical inference. The way this is done, without going into too many details, it's typically that you build a model, a templated model for the distribution of parameters in the underlying distribution. And we also account for selection effects and so on and so forth. So again, I will skip entirely all the details. If you want to know more, there are a lot of papers, or most recently, I've written up excruciatingly long pedagogical overview of this type of analysis if you want to know more. But for today, the only thing I will say is something like this. Basically, to give you an idea, say that you want to measure the mass of the underlying distribution of binary black hole, you could, as LIGO Virgo have done, parameterize it as the sum of 2 components, a Gaussian distribution that could, for example, mimic the presence of a pileup of masses around the peri-instability supernovae, and a power law distribution. Why? Well, because stars seems to follow a power law in their masses. So if you have something like this, then you are modeling the mass distribution of black holes in the universe as a function of 7 or 8 parameters, whatever. And you can measure those parameters from the data. that's what we do within the LIGO Virgo collaboration and in other groups. And you get basically a posterior distribution for the various parameters. Here, for example, I have the Gaussian, the mean of the Gaussian component, the minimum and maximum mass of the black holes in the population, and say the center of the Gaussian. And so you collect a few thousand samples, and then what you do, and that I assume will make clear some of the plots we publish in the LIGO paper, is you draw one of the sample, and because you have a model, the model I showed you previously, you know what that corresponds to as a functional thing that you can plot, is the sum of a power law in red and the Gaussian in green. And then you draw another sample, and another sample, and another sample, and every time you draw the power law plus peak distribution that follows. So as you see, every time you draw a sample, you have different values of the power law slope, the minimum mass black hole, the fraction of black holes in the Gaussian, the center of the Gaussian, and so on and so forth. And when you have collected a few thousands at this point, you have built a spread, and altogether you get an uncertainty on what your measurements of the distribution is. So this is the type of plots you see in LIGO Virgo's paper. And of course, you can do the same thing for the spins. Okay, let me go try to move on. I'll skip this since I see I'm running late. And so just basically to cue Sylvia Stolk, we are now in a situation where we can do this type of analysis, start learning something, because we have roughly 100 compact binaries found in LIGO Virgo data to date, right? And so some of this analysis starts to become possible, even though the individual events may have parameters which are challenging to measure. All right, the last thing I want to say, maybe mostly to make a plug for a session at the APS if you are there in a couple of weeks. Of course, eventually LIGO and Virgo will just saturate how much they can do in the current facilities, and that turns out to be something that make detectable black holes within redshift of 2 or so. But we are designing the next generation gravitational wave detectors. The American design is called Cosmic Explorer. The Einstein telescope is the European design. And a few months ago, Emanuele and Case gave talks that also talked about that type of science. And those detectors, once online in the 2030s, we hope, will be able to detect black holes pretty much up to Z of how much you want, and of the order of 10 to the 5 or 10 to the 6 sources per year. All right, so let me stop here. I have a few challenges with open questions, but maybe we can go back to those if people have questions at the end of both talks. That is my understanding. Before I give Sylvia the microphone, let me, thank Sylvia. And because I didn't mention this, so Sylvia is about to finish, and she's one of the, awardees of an Einstein fellowship from NASA, and will start a postdoc fellowship at Northwestern in a few months. And most of what I told you about would not have been possible without her. All right, I'll stop here. Thank you.
Thanks, Salvo. Okay, I'm gonna take over and share my screen here. Hopefully you can see my slides. Okay, so thank you again to Salvo for that very nice introduction, and to the seminar organizers for inviting us to tell you everything that we know about binary black hole spins following the last observing run of LIGO and Virgo. And this is work that we've done in collaboration with a bunch of other people as well. Okay, so the overview for my portion of the talk. First, I'm going to focus on telling you how well we can measure the spin parameters of individual heavy binary black hole systems. And then I'm going to change gears and tell you about an alternative parametrization that allows us to improve the measurements of component spins for near equal mass systems. And then finally, at the end, I'm going to tell you about some of these population level results that Salvo mentioned, focusing on the magnitudes, tilts, and effective spins, and then on a correlation between the effective spin and redshift for binary black holes. Okay, so as Salvo mentioned, unfortunately, the spin measurements that we've gotten so far for individual sources have been largely uninformative, both for the component spin parameters, so magnitudes and tilts, and for this effective processing spin parameter, chi-p. But recent developments in waveform modeling have led to new approximants that include the effects of both higher order modes and precession in a way that includes the contributions from the full 6-dimensional spin parameters instead of using some reduced parametrization. And in particular, there's this one heavy event that we detected in 03, GW 190521. So this has a total mass on the order of about 150 solar masses in the source frame. And it seems to have an informative measurement of this chi-p parameter relative to the prior. So this was somewhat surprising because, as Salvo showed earlier, it seems like most of the information about the spin should be encoded in the in-spiral portion of the waveform. But for such a heavy system, it merges at really low frequencies in the LIGO band, and we don't get access to a lot of the spin information in the in-spiral. And so how was it possible for us to make a measurement of chi-p for this system if it's so heavy and it also wasn't particularly loud? And you can see sort of a graphical representation of the problem here. This is the waveform for a GW 190521-like system. And if you look early in the in-spiral, you can see these precession cycles that Salvo mentioned. But we, as the LVK, started the analysis at this blue vertical line, which is 11 hertz. And the system merges at about 43 hertz. So we're only able to probe the last fraction of a second of the system. And so we're basically cutting out all the in-spiral, which we thought carried the spin information. So what we wanted to do is to conduct a systematic parameter estimation study of the measurability of spin for heavy binary black hole systems like this using a new waveform model called NR7DQ4. This is a numerical relativity surrogate that's going to be very high fidelity because it's trained on numerical relativity simulations, but it's only valid for systems that have total masses greater than about 60 times the mass of the sun because it only includes 20 orbits before merger. So it allows us to focus on these high mass systems. So the first question that we wanted to ask is which part of the frequency band is actually driving the measurements of spin for these high mass systems? And so to do this, we analyze a simulated signal that has similar parameters to what we infer for GW 190521. And we impose different maximum frequencies in the analysis. So we're always starting at 11 hertz, but then we cut off the analysis first at 16 hertz and then going all the way up to 65 hertz, which is after the merger, because again, this merges at around 43 hertz. Okay, so we start off analyzing this very, very narrow frequency band. And these are the posteriors that we get on the component spin magnitudes and these effective aligned and processing spin parameters. So you'll notice that the posteriors for all of these spin parameters are basically unchanged until you get to these two darkest blue colors. One is the 65 hertz maximum frequency, and the darkest blue includes the whole frequency band up to 512 hertz. So even when we include frequencies after the merger, like 46 and 50 hertz, our posteriors on the spin parameters are still basically uninformative, except for there's some information in chi-effective, but our spin magnitude posteriors are flat, and then our chi-p posterior just looks like the prior. And so crucially, what happens at 65 hertz, if I go back, is that the frequency evolution of the signal changes in time. So here you can see how the frequency evolution changes in time for a signal like this. And when we get to about 65 hertz, we've reached the merger and ring down parts of the signal where the frequency evolution sort of plateaus. And so it seems like including this ring down portion of the signal is crucial to getting information about spin. And this is the part of the waveform that contributes the most to the spin measurement for this type of system. Next, we wanted to sort of generalize this study. So we looked at a broad range of simulated systems. Here we're assigning a spin magnitude of 0.8 to the primary and setting the secondary to have no spin. And then we look at 3 different values of the primary tilt angle, so aligned, some tilt, and then completely in plane. We look at 2 different values of this inclination angle, close to the maximum of that Schutz distribution that Salvo showed, and then very close to edge on. And then we look at two different mass ratios, starting with this unequal mass ratio case, and then a broad range of total masses going from 80 to 240. And so here you can see our constraints, the width of the 90% credible interval of our posteriors on chi-effective and chi-p for all of these simulated systems. And so in general, we find that spins are better constrained for systems that have aligned spins. So you can see that smaller is better on the y-axis here, and we go down to smaller values of this uncertainty as we go to lighter colors for the spin tilt. They're generally better constrained for edge-on inclinations, consistent with what Salvo explained at the beginning. So the dashed lines are generally lower than the solid lines. And then if we toggle between the equal mass and unequal mass case, if you just look at the scale of the y-axis here, especially for chi-p, there's a lot more uncertainty in the equal mass case than in the unequal mass case. And this is just because precession is easier to measure for unequal mass systems, because there are post-Newtonian terms proportional to this difference in mass that encode some of the precession signatures in the waveform. And we also find in general that the constraint degrades as the total mass increases. So even though earlier we were saying that it seems like the ring down contributes the most information to our inferences about spin for these heavy systems, and as you go out to heavier and heavier systems, you get more ring down, it seems like there's still some information that is contributed by the in-spiral, and so as you cut that out, you're losing something there. But as Salva mentioned, even for these very massive systems, we can still measure chi-effective pretty well. So here, our 90% credible interval has a width of about 0.2, which is pretty good. Okay, so to conclude, for this part of the talk, we find that the spin information for these heavy systems like GW 1905-21 depends strongly on the merger and ring down parts of the signal rather than the in-spiral, as was found previously for lower mass systems. We find that the spin constraints generally improve for systems with aligned spins, edge-on inclinations, and unequal masses, but generally get worse with increasing mass across the range that we studied. All right, so now I'm going to switch gears and tell you about an alternative parametrization for improving the measurements of the component spins for near equal mass systems. So typical analyses performed by the LVK sort the components of the binary system into primary and secondary using their masses. So the more massive black hole is called the primary, it's indexed with 1, and our priors enforce that M1 must be greater than M2. But it turns out actually that most of the black holes that we've detected are consistent with having equal mass. So how do you actually distinguish the objects in this case? And how can you actually measure the spin of the most massive black hole, for example, if the two are consistent with equal mass? So to demonstrate this problem, here we have performed parameter estimation for one such simulated system with equal mass. The primary black hole has a spin of 0.8, and the secondary is non-spinning, and the primary tilt is in plane. And so you can see here, if we zoom in on the posteriors for the spin magnitudes, that our recovery of these parameters is confused. We can tell that one of the two black holes is highly spinning, but there's this degeneracy where we don't know which one. The same thing goes for the tilts. We can measure one of the two black holes to have a tilt of about pi on 2, but there's this cross-shaped degeneracy, and it's impossible to distinguish between the two. So what we said instead is, what if we sort the objects by their spin instead of their mass? And so now we're going to define two new parameters called chi-A and chi-B, where A indicates the more rapidly spinning black hole and B indicates the more slowly spinning black hole. So we now enforce that chi-A must be greater than chi-B, and we can also resort the posterior samples for all the other component spin parameters and mass parameters. So we can, for example, define the mass of the more rapidly spinning black hole, MA, or the tilt of the more slowly spinning black hole, theta B. And so when we take our results for the simulated system and apply the spin sorting in green, we break this degeneracy. So you can see that we measure the spin magnitude of the more rapidly spinning black hole very well to be about 0.8 as expected, and the secondary spin magnitude is consistent with 0. And then we're also able to measure the primary spin tilt to be about pi on 2, and our constraint on the secondary spin tilt is consistent with the prior because we think the secondary black hole is non-spinning, and so there should be no information about the tilt. So it turns out that when we apply this spin sorting parametrization generically for binaries that are consistent with equal masses, we get an improvement in our resolution of the component spin parameters. Now, what does this look like for some of the real events that we've seen? We can go back to our favorite GW 1905-21. So in blue, these are the mass sorted posteriors. You can see that there is some support for this system to be very rapidly spinning, but there's also support for it to have a 0 spin. So this is a very broad posterior. While when we apply the spin sorting parametrization in green, we break this degeneracy and we find that one of the black holes is actually very highly spinning. The other black hole has a weak constraint on the spin, but it's consistent with having a small spin. And unfortunately, we don't get a lot of information on the tilts. So in this case, for any event that already had some support for non-zero spin, we can rule out that the more rapidly spinning black hole is non-spinning at 90% credibility. And then for several of these other events that we've detected, we do find a considerable support at the Kerr limit, and that might indicate that these systems are maximally spinning. When we look at systems that we can actually measure to have unequal masses, this parametrization isn't useful. So it tends to introduce the same sort of degeneracies that it breaks in the case of equal mass systems. Okay, so some caveats for this method. It's a very simple idea. It doesn't add new information, and it can be done entirely in post-processing. We're not redoing the analysis with new priors. We're not getting a new Bayesian evidence. We're basically just taking our 15-dimensional blob of probability and slicing it along a different axis. So this just amounts to changing the question from what is the spin of the most massive black hole to what is the spin of the most spinning black hole. And similarly, this does not change inferences about the effective aligned or processing spins. So chi-effective and chi-p are still defined in terms of the mass sorted components, and those stay the same. All right, and now we're going to transition one more time, and I'm going to tell you about the latest constraints on the population level distributions of the binary black hole spins, including the spin sorted spin magnitudes that I just presented. So, as Salvo introduced, to do this population level analyses, we're going to look at all of the binary black holes that we've detected so far with a false alarm rate less than 1 per year as an ensemble. So for analyses that use just GWTC2, these are all the binary black holes that were detected up to the first half of 03, so there are 44 of those. And then GWTC3 includes all of 03, the last observing run, and there are 69 of those. And we're going to account for detector selection effects and the statistical uncertainty in our individual measurements of the spins of these component events in order to get a measure of the true underlying astrophysical distribution rather than the observed distribution. Right, so for spin magnitudes, we typically model the mass sorted spin magnitudes as being drawn from the same beta distribution. So we assume that chi1 and chi2 follow the same generic spin distribution. And you can see some examples of what a beta distribution looks like here. It's bounded between 0 and 1, so it's convenient for analyzing the spin magnitudes, and its shape depends on these alpha and beta parameters. And so here are some different values of these parameters and how they affect the shape. And so as Salvo showed, we want to infer the values of these alpha and beta parameters and then use them to reconstruct what this spin magnitude distribution should be. And when the LBK did that for these last two catalogs, this was the result. So you can see that there's a lot of support at low spins. And in fact, this distribution is consistent with peaking at chi equals 0. So there are some edge effects based on how the analysis and the priors are set up, but really most of the posterior support lies at low spins. And so this tells us that the binary black holes that we're observing in gravitational waves have spins that are smaller than those that have been observed electromagnetically. So this is an interesting discrepancy here. And the fact that we're finding these small spins is consistent with efficient angular momentum transport in the stellar progenitors of these systems. So what that means is if angular momentum transport is efficient, that means that basically all the angular momentum is going to be stored in the envelope of the star. And so when that envelope either gets blown off by stellar winds or gets pulled off by mass transfer, you'll be left with a slowly spinning core that collapses to a slowly spinning black hole. And that's how you might have a population that's born with very low spins. Now, what about if we want to look at the spin distributions of the spin-sorted spin magnitudes? And this might be especially useful if we want to compare against the electromagnetically detected black hole population, because those are always the highest spinning black holes in their binaries. And so here what we do is we infer the distributions of chi A and chi B, assuming that they're the maximum and minimum of two draws from that mass sorted spin magnitude distribution on the last slide. So this is just basically saying that we're going to use order statistics. And here you can see our inferences on chi A in blue and chi B in green following GWTC3. So you can see in particular that the chi A distribution peaks away from 0. And what this tells us is that at least one of the black holes in LBK binaries has some spin. If both of the black holes in all of the binaries that we are seeing had 0 spin or very small spin, the blue and the green would look a lot more like each other. And so this inference tells us that our population is inconsistent with both of the black holes in LVK binaries being non-spinning. Now, what about the spin tilts? Here we typically use a two-component model with a preferentially aligned component, and that's designed to capture the contribution from the field formation scenario, and an isotropic component that's going to capture the contribution from the dynamical formation scenario. And so here again are the results for the last two catalogs. And what I want to highlight here is that there is some evidence for anti-aligned or negative values of cos theta in the population. And so, as Salvo suggested earlier, it's very hard to get such large misalignments with the field formation scenario. And these systems likely must come from the dynamical formation scenario. And so because there is support at these large values of negative cos tilt, some fraction of the population likely forms dynamically. Now, you'll notice that we're also inferring an excess of spins that are exactly aligned to the orbital angular momentum. And so in this recent work led by Salvo, we wanted to see if that excess was actually there in the data, or if it was just being imposed by the model because the model required there to be a peak at exactly aligned spins. And so what we did is we reanalyzed the tilt distribution with many other types of models. And so for the sake of time, I won't give all the mathematical details of what they are, but here you can see our inferred tilt posteriors for 4 different models. And you'll notice that these results are actually quite different from each other. So some have peaks in the middle, one has a peak at the edge, one has more of a plateau. And so what this tells us is that the spin tilt inference is still model driven. Basically, your results are only as good as the model that you put in. And so we still don't have a lot of information about the spin tilts. However, one common feature here is that there seems to be a dearth of systems with very anti-aligned tilts, so cos theta less than about -0.5, relative to the systems that have aligned spins or smaller spin tilts. And so maybe this tells us that there are more systems coming from the field formation scenario than the dynamical formation scenario in this situation. Okay, now for the effective spins, we usually model those as being drawn from a bivariate Gaussian with unknown mean and some covariance matrix. So now instead of fitting for the spin magnitude and tilt distributions directly, we're going to use these somewhat lossy parameters chi-effective and chi-p. And even though there are multiple ways to get the same value of chi-effective and chi-p based on the values of the component spin magnitudes and tilts, these are the parameters that we can measure better, as Salvo said, so we want to look at their population level distributions as well. And here's our inference for chi-p, and you'll notice that it actually peaks away from 0. And so this tells us that actually most of the binaries that we observe have some degree of spin precession, which is very interesting. This is population level evidence for precession in the binary black hole population. We can also look at chi-effective. So our chi-effective distribution notably does not peak at 0. It peaks at positive values of chi-effective at about 0.06. So again, this tells us that there seem to be more systems that have these positive values of the spin tilts, so greater than pi on 2, rather than negative values of the spin tilts. But there is still considerable support at negative values of chi-effective, which is just another way of showing that there's likely some contribution from dynamical formation channels in the population, because again, it's very hard to get these negative values of chi-effective that require really significantly misaligned tilts via the field formation scenario. Okay, so the results that I've presented so far have assumed that the mass, spin, and redshift distributions are all independent of each other. But in reality, we expect that the formation channels that Salvo introduced earlier should impart correlations between these various parameters. And so previous work found an anti-correlation between the mean of the chi-effective distribution and the mass ratio, where more extreme mass ratios had larger values of chi-effective. And so what we wanted to do is to extend this model to look for correlations between spin and primary mass and spin and redshift, or both at the same time. And you can see here what our population model looks like. Again, this is a Gaussian in chi-effective with some unknown mean and width that we want to measure. But instead of just assuming that the mean and width are constant, as was done in the analysis that I showed you on the last slide, we introduced some linear correlation with either redshift or primary mass or both. And when we do this, first by looking for correlations only with redshift, this is the evolution that we infer for the mean of the chi-effective distribution and the width of the chi-effective distribution as a function of redshift. So the mean is consistent with being unevolving in redshift. You can draw a flat line through here, so there's no strong evidence for a correlation. But if you look at the width, and the y-axis is on a log scale here, you'll find that we infer that the width of the chi-effective distribution should increase as a function of redshift out to the maximum redshifts that we can probe with current detectors, which is about 1.8. And so we find that the chi-effective distribution should broaden with redshift at 98.6% credibility, again, when we look only for redshift correlations. And so another way to visualize this is to look at different slices of the chi-effective distribution in redshift. So you can see here, the darkest color corresponds to the closest redshift, and the lightest sort of gray color corresponds to the farthest redshift. And you'll notice that at close redshifts, our distribution is quite narrow, and then it gets broader and broader as you go out to larger redshifts. We can also look for a similar trend in the distribution as a function of primary mass. So again, here, the lighter the color, the more massive the system. And again, we see that the distribution gets broader as we go out to larger primary masses. The correlation with primary mass we find is slightly less significant, so we find that correlation at 93.5% credibility. And so we wanted to see if we could determine which one of these parameters, redshift or primary mass, actually drives the correlation that we are seeing. So when we look for correlations with both parameters, we find that no correlation with either is disfavored at 96.2% credibility, but our measurement is degenerate, and we unfortunately cannot tell which at this stage yet is really driving the correlation. Now, you might be thinking, isn't there a way that your analysis can be tricked into finding a correlation when there really isn't one in the data? For example, the systems that we detect at larger redshifts are likely going to have lower SNR, and so we might have a less constraining measurement of chi-effective for those systems. Couldn't that falsely manifest as a correlation? And so we wanted to check this, and to do this, we design a simulated population that's similar to the real data that we have from GWTC3, but we can play God basically and set the parameters of the population distributions. And this time we're going to enforce that there is no correlation in this simulated population. And when we take our simulated population with no correlation and look for correlations in the same way that we did in the real data, these are our inferred chi-effective distributions as a function of redshift and mass. So you'll notice that these look quite morphologically different from what we got for the real data. The distribution starts out broad at the closest redshifts, then gets narrow, and then gets broad again. And the same thing happens for the primary mass correlation. And there's also significantly more uncertainty in these slices than we got in the real data. And so this is telling us that our method is not going to be tricked into finding a correlation when there isn't one. Okay, and so you might be wondering, this is great, but what does this actually tell us about astrophysics? Can we learn something from this? And so I'm just going to take a bit of time and tell you about the astrophysical implications of what we found. So we think that if what we were seeing is a changing mixture fraction between the contributions from the different formation channels, that would preferentially manifest as a correlation between the mean of the spin distribution and redshift. So for example, if we have more binaries forming in the field formation scenario, those are going to have preferentially positive spins. If there are more of those at high redshift, then the whole spin distribution would shift towards larger values at larger redshifts. But that's not what we see. We see it sort of get symmetrically broader. And so we think that the broadening is more likely to be explained in terms of a change in the natal spin distribution with redshift. So one possibility for how this might work is that it's possible for the second-born black hole in the field formation scenario to become tidally spun up due to interactions with the first-born black hole. So the progenitor star of the second-born black hole can become tidally locked to the first-born black hole in the orbit. And so the efficiency of this tidal spin-up depends on the separation. The closer they are together, the more efficient the tidal spin-up, but also the faster they merge. And so they'll have a shorter delay time, which means they'll merge at a higher redshift. Alternatively, there's a relationship between metallicity and the efficiency of angular momentum transport. So lower metallicity stars are born preferentially at higher redshifts, and stars with lower metallicity have less efficient stellar winds. And so those stars will have less of their angular momentum basically blown off in the envelope. And so they might actually form directly as rapidly rotating. And that's another way that you could possibly get a correlation like the one that we're seeing. And then I just want to highlight that we've only found this correlation at about 2.5 sigma significance, so it's comparable to other correlations that have been found, but we still want more data to see if this is a real feature or if this is sort of a statistical fluke based on the 69 events that we've analyzed. All right, so to conclude this section on population level distributions, we found that at least one of the black holes in LVK binaries has spin, but spins generally are small. And so this is consistent with the idea that there is efficient angular momentum transport in the stellar progenitors of these black holes. We've also found that the spin tilts are drawn from a nearly isotropic distribution, and so there's population level evidence for spin precession and the presence of extremely misaligned or negative spins. And this indicates that there's likely some contribution from the dynamical formation channel. And then finally, we found that the aligned effective spin distribution likely broadens with redshift, and this would be indicative of a change in the natal spin distribution over cosmic time. And so at the end, I want to tell you what I'm excited about for the future. So the LIGO and Virgo and Kagra detectors are going to turn back on at the end of May next month for the start of 04, and we're going to expect to detect about 1 binary black hole per day. So as we saw earlier, some of our conclusions based on the 03 data are still model driven, the spin tilt distribution, for example. But hopefully with this improved detector sensitivity, we're going to get more detections and smaller statistical uncertainties for our individual event measurements, and that will translate into better constraints on our population level distributions. We might also consider alternative approaches to these phenomenological, strongly parameterized models that I described. So Salvo skipped over a slide on these non-parametric models, like using a spline to fit a generic shape to the distribution, or using a Gaussian process. So these are going to be more flexible. They're going to tell us exactly what's in the data, but they're more difficult to interpret astrophysically. So it's sort of harder to learn about the physical processes. Now, the opposite is true if you take the alternative approach of directly parameterizing your population model in terms of theory. These are less flexible because you have to take exactly the output of your population synthesis code, but it's more intuitive to actually trace that back to some astrophysical statement. And so a few of the questions that we've still got spinning at this time are, why does the spin information seem to come from the merger and ring down for some of these individual heavy binary black holes? How exactly is that encoded in the waveform? Is spin tilt really a reliable tracer of binary formation channels? Are we going to be able to use that to say something about how binary black holes form, hopefully during 04? And then why are the spins of binary black holes different than those that we observe electromagnetically? And could we potentially use spin sorting to break this conflict here? And with that, I'm happy to stop and take any questions on both parts of the talk as well. Thanks.
Thank you so much. Great talk to you both. We appreciate it. If anyone has any questions, they're free to type them in the chat and I can read them out, or they can ask them themselves. I'll call people out as they raise their hands. I see we have one from Leo.
Sorry, I was just trying to hit the clap emoji.
Oh, you might have. I might have not realized what emoji I was looking at as I was speaking quickly. Maybe I will start with a question if you don't mind. So you mentioned this question about wondering if the spin tilt is a reliable tracer for formation channels. I'm not an expert in gravitational wave signals and such myself. So are there other parameters that could be tracers that one could try to pull together information from to help sort out the formation channel question?
Yeah.
And if so, what are those?
I have one. I was typing it, but if you want to hear it outright, I was wondering, when you talk about spin, if you're just talking about
excuse me, Lee, is this the same question that I just asked? Are you piggybacking on it, or do you have a separate question?
I'm not sure what you just said. I'm sorry, I was busy thinking and trying to type. I didn't hear what you said. Let me have them answer the question I just asked. You can finish typing yours, or you can ask it after they've answered. Okay, I'll type it. Thank you.
So, yeah. Right, my question was, are there other parameters one could try to?
Yeah, so Salvo mentioned briefly eccentricity, which is probably the most clear tracer of binary formation. I don't know if you want to put that slide back up, Salvo, but basically, if there's any sort of noticeable eccentricity in the system, that's going to be smoking gun evidence for dynamical formation, because we expect the field binaries to have circularized by the time they merge. Unfortunately, we don't have reliable waveform models that include both eccentricity and spin precession at the moment, and so we probably won't be able to get a population level measurement or individual measurements of this parameter that are reliable in the near future. I don't know if Salvo wants to add anything.
Yeah, maybe I'll just very quickly also add that, so of course I agree with what Sylvia said. The other thing, Dalia, is that as Sylvia mentioned toward the end of the talk, we are now in a position where we can not only start or trying to measure the properties along these rows, which I've drawn here, but also how values in different rows are correlated to one another, right? And that, of course, it gives you even more information. So not just only is the eccentricity large or small, but is the eccentricity large or small depending on whether the mass ratio is large or small, say, or something like that. And in that case, though, I would say that the limiting factor, it's both on our side because we don't have enough events and reliable waveform to do so, but and that's just my personal opinion. I think also on the population synthesis side is like codes I was mentioning earlier, some of which I have here. I don't think they are yet either at the stage where they can make extremely reliable prediction about things like correlation, and not because they're lazy, just because it's a very hard problem, right? So if you ask me what I think will happen in the next few years, it's some sort of positive feedback loop where these codes make some prediction, we detect the next 200 events, and some of these will have properties that agree with the prediction. Some can be made agree by changing some knob, and then you do this a few times and hopefully will converge to knowledge.
Thank you. Okay, Lee, you can go ahead and ask your question if you'd like.
Okay, I just wondered, when you talk about spin, are you talking about intrinsic spin of black holes, or are you just talking about the angular momentum, which is conserved in the merger of the two black holes? That's an important difference. And I'm going to make a little comment, although we're running low on time. It's in the case of electromagnetic, particles, and what I'll say, things like atoms that form. We're talking both about the angular momentum, but also the individual particles have intrinsic spin. And I'm wondering if you're talking that way about black holes. So that's what I'm asking is, when you talk about the angular momentum, are you talking about basically the orbital angular momentum, or are you talking about some sort of intrinsic spin that you're assigning to the black holes? Go ahead, tell me.
Yeah, so spin is basically one of the two fundamental properties required to describe a black hole, mass and this intrinsic fundamental spin of the black hole. For example, when the binary system merges, orbital angular momentum has to be conserved. And so the resultant black hole, its intrinsic spin will absorb the orbital angular momentum. And so it will inherit spin in that way. But here we're talking about the intrinsic properties of the individual objects.
Okay, I'm just going to tell you a little bit about this. My background is actually in atomic physics, and so I'm kind of into what I'll say spin and angular momentum. And what I'm going to tell you is that as the merger takes place, as the orbits decay down to a merger, that angular momentum that's involved with that is actually given up in form of radiation, probably gravitational radiation. And so eventually when you reach what I'll call a ground state and the merge takes place, there's very little angular momentum left because it's all been radiated away in terms of gravitational radiation, which has naturally gravitons have the spin too, so that they basically are carrying that angular momentum away in the gravitational radiation. Am I just totally off base here, or tell me?
So no, Lee, I think you are right, and I want to say that the gravitational waveforms that we used, which are based on numerical relativity simulation, do correctly account for the fact that gravitational waves carry away some of the angular momentum originally present in the orbit. So that should be dealt with in the waveform we use in a self-consistent way.
Yes, that's all. Thank you. I just wanted to kind of point that out because it seemed like you were talking about something that I'm not sure completely exists. Certainly you can get to the point in what I'll say the ground state before the merger. You can get to the point where there is still some residual angular momentum, which then it goes into the merger. And then
yeah, so we
merged
expect
object has angular momentum.
Yeah, that's right. So we expect the merger remnant, if the two black holes initially had 0 spin, the merger remnant is going to have a spin of about 0.7 intrinsically because of the conservation of angular momentum in the merger.
Yeah, okay, thank you. I'm just trying to help you out a little bit, also help myself out a little in understanding. So thank you. That's the best we can do right now.
Thanks. Delilah, looks like you're muted. Delilah, looks like you're muted.
Oh, thank you. Sorry, I was going to say, is there any more questions that anyone would like to ask our gracious? Any more questions? All right, then. Thank you so much to our speakers once again. It was a very informative talk, and as well as one that's exciting as far as looking forward to what we'll be able to learn about populations of binaries, especially with the new run for LLVK coming up. Thank you so much, everyone who joined as well.